All right, section 13.3 is partial derivatives. Partial derivatives come from the fact that we are looking at a three-dimensional or higher shaped curve now. So let me start by talking about what's going on here. So when we looked at how functions change, we considered derivatives. And understood that dy dx, also called f prime of x, was the limit as, we'll go with x. X goes to, sorry, not x, h here. H goes to 0 of f of x plus h minus f of x over h. We will now generalize this idea to 3D, 3 dimensions, by considering how a function, now it's a function of two variables or more, but how a function changes when one variable is held fixed, or you can use the word here constant. This is called the partial derivative. First thing I'm going to do is I'm going to write down what the definition actually is a partial derivative. This isn't a definition. This is sort of developing the idea conceptually of what we're going to be doing. Let me write down what the actual definition looks like for you. So this is definition 3.1. The partial derivatives of f of xy. I don't know why I said derivatives is derivative. There are two partials, but only one of them is this one. The partial derivative of f of xi with f of xy with respect to x is written. Okay, so there are two ways to write this, at least two, but there's two that your book is going to commonly use. So one of the ways that we wrote derivatives before was dy dx, right? And another way we wrote was f prime of x. Well, dy dx looks like this. This is not a d. I'm having a difficult time remembering what Greek letter this is. Do you guys remember? Is it sigma? Delta. I think it's delta. I think it's lowercase delta. That's what I'm remembering. Okay, I could be wrong though. All right, I put the x in the wrong place in talking about that. So we have a partial of f with respect to x. So it looks like the d's that we used before, okay, but it's not a d. You also, we can't use f prime. That doesn't work. because we have to identify which variable we're using as our variable. So what we do is we use a subscript instead, and we designate the subscript as the variable name that we're using, so f sub x. Okay, so either of those notations are notations for what we're going to do. You may see the xy written next to it, like you see functions sometimes written with the xy next to them. If you leave that off, that's fine with me too. It's not a deal breaker because you see them written both ways. But this is the limit as h approaches 0 of f of x plus h comma y minus f of x y. So notice, what's wrong? Did I do something wrong? I thought somebody was telling me I did an error. Oh, gotcha. Okay. All over h. So you'll notice the only place that I have a plus h in it is with the variable x, because I'm holding the y as a constant. It's not changing. Okay, so it's acting like a constant. Similarly, we can talk about the partial derivative of f of x with respect to y, and we can do delta f delta y, or we can call it f sub y, and the limit as h approaches 0 of f of x y plus h minus f of x y over h. So you ready for the best news of the day? We're not going to do any of these with limits. We're going to do them with derivative rules that you know and love and have been using now for 2+ years, some of you. Okay? We're not going to do these with the limits. But this is how it's working, okay? Let me know when we can move to the next slide and we'll go to there. We're good? Everybody has it? Okay. All right, so we're going to do example. We're going to find all, and this word I haven't clarified yet, but I will, first order partial derivatives. It's like saying first derivatives. It's just the first order derivatives, okay? So we're going to find the partial derivatives, which are going to be the first derivatives of f of xy. The function we're going to work with is x squared sine xy minus 3y to the third. It says find all first orders, which means I'm going to have to find how many? Just 2, because I only have 2 variables, input variables. I have x and I have y. So I'm going to find f sub x, or delta f, delta x, and f sub y, or delta f, delta y. So I'll go with this notation on this one. We'll do f sub x. So x is my variable, okay? Which means I'm treating y like it's a number. All right, it is not a variable as I'm working through this particular problem. So starting with x is the variable, I have 2 pieces of this function that are multiplied and they both have x in them, which means I'm going to be using the product rule. Product rule because there's product, right? Okay, so the product rule, again, depending on which piece of it you want to do first, one component is held fixed, x squared I'll do, and then we need the derivative of the sine xy. So what's the derivative of sine? Cosine of xy. And then what's the derivative of xy if x is the variable and y is a constant? Just y, right? So I'm going to put parentheses here and we'll simplify it in a minute. So times y, that's from the inside. That's half of it. The other half's easier though. So now I need the derivative of x squared, which is 2x, and then I hold the sine xy constant. Not constant, I'm sorry, I don't mean to say that, but I hold it fixed, I don't change it. Now, what would the derivative of the 3y cubed be? That's 0. Why? Because y is just a number in this operation right now, right? Y is held constant. Derivative of constant is 0. All right, so simplifying this just a touch because it looks a little bit messy, we would have x squared y cosine xy plus 2x sine xy. And if you give yourself enough space, you probably can just jump straight to there instead of having to write it twice. F sub y. All right, so f sub y. Now going back up to our original function, there is a y right here in the inside of this, which means everything else is constant, right? The x squared at the beginning is a constant. It's just like having a number at the beginning. So I do not have a product rule on this problem for y because x squared sine xy only has one y there, which means the x squared stays put because it's constant, it's a number. And the derivative of sine is cosine of xy. And then I need the derivative of the xy, but this time x is constant and y is the variable. So x, right. The derivative of xy would be x if x is a number and y is the variable. All right, the other piece, and that's it. I mean, that's the whole piece of the x squared sine xy. The other part of it, negative 3 y cubed. What'd I get? Yeah, negative 9y squared. And I'll take just a touch to simplify this. I can actually have this as x cubed cosine xy minus 9y squared. All right, let's do one more. I don't think I have space here. Let me try that again. Same directions. I'm changing your function. F of xy is going to be 4e to the negative x over y plus 1 over y minus 4. It might be helpful to think about this because we're going to be working with derivatives as negative x y to the negative 1. Potentially even, depending on what kind of a viewpoint you do, you might want to think of this one like that. You could do that. So whichever viewpoint you want to use is fine. All partial derivatives. So we're going to first find f sub f. You know what? I'll use the other notation just for fun. So delta f delta x. All right, so the first piece of this function actually has x and y in it, so it's going to have, it's not going to be 0. The 4 is just a number, so it's going to be 4. Anytime I have a derivative of e to a power's derivative is e to that power. So none of this changes. The part that's going to be changing, though, is what's the derivative of negative x over y. If x is the variable and y is held constant. Negative 1 over y is correct. So this is equivalent to having something like negative x over 4, right? What would the derivative of negative x over 4 be? Well, it'd just be negative 1/4. And y is acting like the number 4 there. Okay? Excellent. What about the other piece? 1 over y minus 4. That's 0. How come, Jordan? Yeah, it's all constants, right? There's no variable in that. The variable's x in this particular problem. All right, so rewriting this a little more cleanly, we would have negative 4 over y, e to the negative x over y. All right, let's do delta f delta y, which is the harder piece on this particular function. We still have the 4, we still have the negative, or the e to the negative xy. None of that's going to be any different. The part that's going to be different, though, is the derivative of the negative x over y. So I need to know what is the derivative of negative x over y, and or you could think what is the derivative of negative xy to the negative 1. What was it? What do you have? X over y squared. Does everybody agree with that? Yep. So, and if you think about it, I kind of like it written in this notation right here. I can multiply by the -1, so the negatives go away, and then this is xy to the -2, and so we've got x over y squared. So whatever of that you need to show yourself to make sure that you've got those details, you're in good shape. What about the other half? What's the derivative of y minus 4 to the -1, or 1 over y minus 4?
Over y minus 4 squared.
It is. 1 over y minus 4 squared. If you're thinking about it in terms of the way I wrote it on the very top here, it'd be -1, it'd be y minus 4 to the -2. The derivative of y minus 4 would just be 1, because it's just plain old y by itself. So you're going to get the -1 on top. Did I miss a negative?
Yeah.
I did. There we go. So you're going to negative on top, or I'll put it in front, and then you've got the y minus 4 squared on bottom. Okay, so just a touch of simplification. We can write this then as 4x over y squared, e to the -x over y, and then minus 1 over y minus 4 squared. The hardest part about doing this is telling yourself which one's the variable and which one's the constant and remembering it as you work. You guys know how to find derivatives. But holding something constant when it looks like a variable is a little tricky after you've not been doing that for so long. So that's the trickiest part. We're not going to do an example, but I'm going to have you go ahead and write down about 3 sentences here, and then we'll stop, okay? So we aren't finished with this section, so you only have 1 homework set over the weekend. I will go ahead and write down the homework set for this if you want to start it, because you have a lot more time between now and Tuesday than you do between Tuesday and Thursday next week, and we definitely will finish this on Tuesday and another section. So I'll go ahead and give you the homework. But let me go ahead and tell you what's up in the other part of this section. So similarly, we can talk about second order. Partial derivatives. So one of those is delta f, and you put the squared between them, and then the delta x, and you put the squared, it looks like, on the ends. This is the second partial of f with respect to x twice. You guys remember doing that when we did derivatives before. It's a very awkward kind of a phrasing. The notation is a lot easier to look at like this. This is f sub xx. Okay, it's a second derivative of x. So what we're doing is we take the second derivative, we'll say it this way, we take the derivative with respect to x twice. So we're doing 2 derivatives, and x is the variable both times. We can do the same thing with y, right? So we can do d2f dy2, which is f sub yy. And this sentence right here looks exactly the same, except for we do it with respect to y twice. But it gets a little more complicated, because what's the other option here? Yeah. So we can still do a second derivative of f, but we could do it with respect to x or with respect to y in either order. And these are not always the same quantity. They are a lot of the time, but they are not always. So dy, whoops, that's d, x. So the first one here, and this is where the ordering gets a little bit funny. Let me actually write this carefully. This is actually the derivative of the derivative with respect df dy. So what you're actually doing here is you take the part in the inside first. So you do in this here, this is the partial with respect to y first, and then you take the partial with respect to x after that. So in terms of that notation, it actually switches, because in this notation, we write the first one we do first. F sub yx means take the first partial with respect to y, and then the second partial with respect to x. So we're doing it in the other order. So the same thing happens down here. This is delta f delta y of delta f delta x, which is actually f sub x y in reverse order. I'm not a fan of the notation switching, but that's why they're switching. It's a little awkward. So I have a couple examples we'll do of second partials next time, but let me go ahead and give you the homework. You'll know exactly where the homework stops from being first partials and turns into second partials because the directions change. So does everybody have this written down? Okay, I'm going to put this on the next slide. So this is page 841. 2, 3, 4, 6, 9, 12, 13, 14, 37, and 51, 52. And these are a little different, and we'll talk about them next time. You're not going to get that far anyway. There's no need to it. I think it's 2 through 6, or maybe 2 through 9. Maybe 2 through 9 is the first partials. So the first 4 or 5 problems is the first partial derivatives you could do if you want to get that started, okay?